yeah, so we're going to be talking about these double degenerate systems as candidates for progenitors type 1As. So I'm going to start with a little bit of a review of 1As and why we care about them. Mostly because they're cosmological tools, and everybody cares about cosmology. They're good for distance indicators, and they probe the low mass star formation rate at high Z. That's typically how we measure star formation rates. 1As is the brightest thing you can see at that distance. And there's significant contributors of iron developments, and presumably predominant contributors of iron developments, especially in Europe. So without them, we wouldn't understand where all the iron comes from. So a 1A, and here's that compilation of a bunch of data samples. This is Octopus, the redshift. Okay, so 1A is powered predominantly by the decay of nickel 56. This is a radioactive decay. The half-life of nickel 56 is about 6 days. And then this cobalt 56 will also decay to iron 56. This is the predominant production of iron 56 in the universe is from this process coming from 1As. And a typical 1A produces roughly about half solar mass of nickel 56. Sometimes as much as 1, but typically not more than that. And you can think of that if you burn an entire white dwarf can only be multiplied by 4, that's the Chernusik mass. If you burn an entire white dwarf at the Chernusik mass near first statistical equilibrium, you can't really get much more than 0.9 solar mass of nickel 56 anyway. So this is not surprising that typical supernovae, type 1A supernovae, don't produce much more than this. And the picture that most people have in their minds for where 1A progenitor is the single degenerate scenario. And this is actually what you first Google hit when you type in type 1A supernova, you get this image of white dwarf accreting from solar ball companion, accreting helium. There could be Novae events earlier, but this is then accreting at some specific rate that it gives you type 1A supernova. And Emoto, back in the 90s, did some analytical calculations for what kind of accretion rate would give you type 1A supernova, as opposed to giving you this, I guess, would be Novae here, where you're actually then removing mass from the white dwarf. And then if you accrete too fast, then you just burn the carbon into oxygen and magnesium, you just turn up a different kind of white dwarf. And if you get accretion, you just collapse in all these other parts here. Now, the only reason I show this plot is because this is a small region of this parameter space to hit for single degenerate scenarios, and this is only for single degenerate accretion. But we know from type 1A rates that 1 out of every 100 white dwarfs has to become a type 1A supernova. And this is a small region of parameter space to hit to get that kind of rate. So the suggestion is, and it might just be fashion, but the suggestion is that double degenerates then must play a significant role as contributors of type 1As. And you might ask, do we have any evidence that the double degenerate scenarios make any 1As? And we actually do. So all of these supernovae are exceptionally bright, and they've been attributed as double degenerate events. And the best indicator, well, for instance, this supernova right here, this 2007 IF, had 1.6 solar masses of nickel. And since the Chernusik mass is 1.4, if you have more than 1.4 and it's all nickel, you obviously have 3 white dwarfs involved. So this one is certainly a double degenerate event. The rest of these are technically double degenerate events, also because of nickel 56. Many of these, when they look at early spectra, you see unburned carbon and oxygen in their spectral lines. And that's an important thing that I'll come to later. And then these other supernovae are exceptionally dim, and these aren't typically set to be double degenerate, but as we'll see, the double degenerate scenarios can span the entire range of brightnesses. Whereas in the single degenerate scenario, if you have to get to a Chernusik mass, it's probably always going to be the same brightness or this. And then if double degenerates then are masquerading as typical 1As because they're at typical brightnesses, the entire brightness range, then it's not clear, or at least it's not obvious, that you would be able to correct them with this Phillips direction in a cosmological design. And when we do correct supernovae where we've excluded the obvious double degenerate candidates, there's still 15% dispersion in the light curves. And so it would be nice to have really clear signatures of double degenerate scenarios, and to check whether double degenerate scenarios are correctable this way. That's still not clear. So the first double degenerate scenario we'll talk about is the collisions, because these are the rarest, so I'll get them out of the way. And you know, stars don't collide very often, so you might ask where the heck would these ever collide, and the obvious answer is they would be doing it in Cosmological clusters. So this is a Hubble image of nearby Cosmological cluster. All of these boxes and circles are white dwarfs. I think the blue means they're young and the red means they're old. But in any case, there's a lot of white dwarfs in this tiny little box, and we can't even look in there where there would be many more white dwarfs. And the collision rate would go up. And so you could do a sort of back of the envelope calculation using gravitational cross-section. The escape velocity of a white dwarf is about 4,000 kilometers per second. Velocity dispersion in Cosmological clusters is about 10 kilometers per second. And then you can use a conservative estimate, or my conservative estimate, for the number density of white dwarfs, just using a saltpeter ion math. And you get that about 10 to 100 collisions per year at redshift less than 1, which is not a phenomenal rate, but it's not negligible. I think, I was talking to Martin about this yesterday, I think the total 1A rate at this same redshift less than 1, is about 10 to the 7. So this is 1 out of every 100,000 would be a collision. But I think that's really nice. And you could ask, well, do we even have 1As in Cosmological clusters? And here's definitely a confirmed supernova remnant in a Cosmological cluster. And if you have supernova remnant in a Cosmological cluster, it's probably 1A. It's very unlikely that 4 clusters in a Cosmological cluster. So all those stuff with it. And then Peng et al. In 2004 have what they think is also supernova remnant, but that evidence wasn't quite as clear as this comment. So the earliest work in modeling these collisions was done by Benz. It's like the earliest work in anything was done by Benz in SPH. And he collided 2.6 solar mass white dwarfs using 5,000 particles total with SPH. I guess we should say SPH is a Lagrange shooting particle code, where you had particles as your interpolate. Technically so. And so he had 5,000 particles, and you can see he produced a sort of remnant here, and almost no nickel, right? Less than a tenth of solar mass of nickel. And so he said, well, this is irrelevant. This is something that would be invisible. And we moved on. But this was 1989. We have faster computers now, better equation to state. And so this problem has been revisited. Besides by ourselves, it was revisited by Raskin et al. In 2009 and Monaguilar in 2010. And for our case, we use SNSPH, which is from Los Alamos. And we use 2 million particles, much more than the 5,000 that Benz used. And we use more mass combinations than either of these two groups in Benz. So here is a slide from one of these simulations of the collision. This is 2 roughly 0.6 solar mass white dwarfs. It's actually 0.64 each. And on the left here, I've plotted density versus temperature, and then I color code by predominant composition. So green means it's unburned carbon and oxygen. Red means it's silicon, and then as you'll see later, blue means nickel. So at the initial stages of the collision, you have these 3 regions. You have unshocked material, unburned, and unshocked. So that would be all this stuff here. You have some shocked material that's not burned. So that would be this material here. And then you have some material that's burning silicon, and that's mostly around the center here. And at the initial condition, or the initial collision, the inflow velocity is actually greater than the sound speed of the white dwarfs. Since the sound speed of white dwarfs, especially for these, is roughly the same as the escape velocity. When they do collide, then you get a stalled shock. So the shock is not going away. You're just simply piling more material into it.
Temperature scale here. So naively, I would have thought that if the degenerate white dwarf, the shock, the entropy doesn't matter all that much until you live this degeneracy. I would have thought degenerate matter are kind of sitting at the same entropy. So you're saying that the shock actually is enough to lift the degeneracy on the gas?
Yeah.
Yes.
Yeah, well, I mean, to some extent. When you change the energy very slightly in the degenerate material, you can change the temperature by an order of magnitude, just by changing the pressure.
Temperature changes, but the pressure, which is what matters, does not change that much.
I'm sorry.
I mean, the pressure doesn't, the temperature can change, but the pressure doesn't depend on the temperature anymore.
That's right.
Degenerate matter, so.
You're dropping these basically, right?
Yeah.
I mean, from nearly a rest of
yeah.
And so you're liberating very binary stars. So we expect those events to be more or less like, in order of magnitude, it's not, non-degenerate.
Right, it's not non-degenerated, that region yet, right? It's close to it, but it's still
Yeah,
degenerate.
this is not degenerate, but this is still degenerate.
Still degenerate.
And yeah, all I was saying, it doesn't take very much to get material to get a lot of energy to get this temperature.
Yes, of course, the changing pressure, which is by the fact the hydrodynamics is small, even though the temperature is large.
Right, yeah. Okay, so if we advance, this is about a second later. And so now you can see some nickel showing up, and it's actually here in these two little white spots, which are larger on my screen than I have here. But there are two separate detonations occurring on this shock front here. And you can see that up here in the plot of the sun speeds going on. And so for this combination of masses, quite six solar masses, you get two separate detonations. They'll start to burn some nickel.
So zero impact parameter. It's
Zero
equal mass,
impact.
zero impact parameter.
Yes. And then so the detonations will expand and cross each other. It's not clear to me whether this is a reflection or a crossing. Much better visualization to see that, but I think the effect is the same. And then those detonations will just expand out on line side and go a lot of it into nickel. And so I have an animation of that happening. So sort of real time. So you can see the detonations starting here, two separate detonations, bringing some nickel up here. So yeah, if I introduce an impact parameter, I still get two detonations. You can see them here, these two blobs here. But because I have this impact parameter now and I have some shear, these detonations still travel through the densest material first, so it's not too nice to impact parameter. Let's see what the speed of shift is. But in the end, it's still a spherical explosion, so even though it's so if we look at the distribution of isotopes after the detonation, so you're looking at now the supernova remnant, you get the same onion layer effect that you would expect from a typical 1A. So you have nickel 56 in the center, and this is all going to be contained into cobalt 56. You get some silicon right outside that, and then this is the important new feature, the sunburn carbon and oxygen, that we saw was an indicator of double coherent observation, and not necessarily a truthful supernova 1A. So that was interesting. So you could ask, why are we getting such a different answer from bands? And we did do convergence tests of x direction, so I said we did 2 million particles. Here's our convergence using nickel 56 as an indicator of convergence. This red line is old simulations where we had done a different kind of But where does Ben sit on this plot? Well, there it is. It looks like he was roughly on the right track, but he just didn't have the computer that could do it. So it wasn't wrong. He just wasn't convinced.
How many data points in the book you put? Just by simulation?
There's one here, here, and then there's one there, I think, and one there. So now if we try disparate masses, they're not equal. What we're getting is different. And you can see here, so this is 0.8 and 0.6. This is the 0.8 here, white force. There are more mass than smaller. And at first you get a detonation on the side of the less massive one. And that detonation sends a shock through this shock region, this region 1, which instigates another detonation on the other side.
Question, why is the surface just mottled with things?
That's an artifact of SPA and of the visualization, which I wrote myself, so I could find a better one that wouldn't look like that.
And I'm trying to think of the number of particles, yeah, that's more or less the exact.
Yeah, so it's 1 million particles per star, and most of them are in there. In the center, so. So here's the even more disparate masses now. This is 0.6 and 1.0, roughly 1.0. And a similar sort of thing happens where you create a detonation shock on the side of the less massive white dwarf almost immediately, because it doesn't, the density for the 1.0 is already really high, and that will propagate this way. It will send a shock back to here and here another one. So on and so forth. So I have a movie. This isn't scientifically instructive, but it was interesting. And this is that same combination of 0.6 and 1.0. I don't know why I didn't finish, but this one, it goes in, this is all material that's just ejected from the collision. The detonation is now happening inside. There we go, and it blows it all out. And typically this movie goes on a couple more seconds, and I think it's just popcorn or something, but there's like a jacket or something. So if we add impact parameters to these disparate mass combinations, then, for instance, for this one, we get one detonation on the side of the less massive. But now the shear force is going to twist this detonation around and cause these weird configurations. So now, if I should bring up the case of when you have two equal masses but they're more massive, the detonations, rather than appearing on the sides of these shocks, actually move toward the center. And for this case, of 2.8, we kind of see there are multiple detonations happening here. So it's kind of a column of detonations that then superimpose to be straight. And then with the truly massive ones, it doesn't even matter what impact parameter I throw them together. This is an impact parameter of 2 white dwarf radii, so the most grazing collision you can get, and they still move. So what comes out down here, that's not a star. That's just hot material.
That's fun.
That's just hot material. It's ejected from the detonation. And that's very unlike these less massive ones, but throw them together with a similar impact parameter. You see it right. And that's mainly due to the more massive ones being so dense on the surface that it doesn't take very much to create detonation.
Do you have a sense of what the critical mass, combined mass for detonation is?
At 0 impact parameter or at a high impact parameter? Well, I mean, I did put together a grid that maybe we could height it out what it would be, but so this is just a field for all of these combinations. And the key takeaway points are that for these massive combinations, it doesn't matter what impact parameter I use. You get basically the same field. And they all fit. And then the other key takeaway is that there's a minimum mass, so this was a combination of two very low mass white dwarfs. They did detonate, but they didn't silicon burning was enough to unblind the stars. And then the last thing is that many of these low mass combinations at high impact parameters form remnants, which then look very much like merger remnants.
So it takes 1.06 into 0.64 and you merge them. So you get most part of it which went away and part of it which stays behind, or what happens then?
So a lot of the 0.64 will burn away, and this one is mostly intact, and it just sits inside it. So the next one I'll talk about is the one that most people care more about, is the burgers. still preliminary work, so I don't have a lot of results, but I think there's some cool movies. This one I'm just going to show first because it's not carbonosity, so I haven't quite figured out how to interpret this one yet, but this is if one of the white dwarfs was helium, and so this one is helium. You get something interesting. You can see it's sort of multiple detonations here until it flies up the accretion sphere, detonation part of the accretion sphere. This stuff here is kind of trapped in the L3 point, and now the L3 point's gone, so it will just fall around that new stuff. But that's a strange case that I've only got one on. So most of them have been these carbonosity and carbonosity. And when they merge, they don't really do very much. It's interesting. They just sort of, this movie usually goes on longer, but you get a remnant. So this is a cold core with a hot disk around it. Similar thing happens in the 0.96, where they're both equal mass. So now this mass combination is an interesting one to try because there is this other result from Packmore et al., where they merged two 0.9 solar mass stars, and they picked conditions that on a macro scale they assume that microphysical conditions would lead to a detonation. So this is conditions that other simulations have said that if you have this temperature and this density, then smaller scale situations than you could possibly resolve in an SPH simulation would lead to a detonation. And so they inserted one when they found those conditions. And so I ran this as a test to see if I get the same thing. So I basically get the same thing. These little flecks of brighter spots here are material that is burning and is extremely hot at roughly the same conditions that Packmore et al. Found in their simulation. So I'm basically reproducing what they did, I just don't insert that energy. And so they carried this simulation then on into a grid-based code after inserting like that, which is see what that would be. So my approach going forward is going to be a little bit different. I'll just say with the preliminary results of these mergers has been that there's non-explosive carbon burning on the surface of the primary. I neglected to mention that even when I'm doing carbon oxygen, I do have helium atmosphere. That helium all burns away carbon right away. So it doesn't really affect anything. And you're left with these cold cores with these hot disks. I guess because I'm a scientist, it's my job to take something cool like this merger and turn it into a boring graph. So this is what I've done here. This blue is temperature on a TPM scale. So you can see the temperature is about 10 to the 8 in the core, and then it's very hot in the disk, 10 to the 9. This is roughly the disk core interface here.
How much mass in the disk?
It's basically whatever the mass of the other companion was. The star in the center is, or the primary one, even in a equal mass scenario, it's not very much disruptive. And you can kind of see from this radial point, I don't think anybody has committed to memory the radius of the 0.91, but it's about that.
So the bigger white dwarf is being heated inside. It's being heated by shock. Weak
Like,
shocks.
what's that?
It's being heated by weak shock.
Yeah, we shock from the accretion stream, but not very much. It's only 10 to the 8, so it's not quite even carbon burning. Yeah. I think that the initial condition for this star is 10 to the 7. So yeah, we needed a little bit. Not very much. So where I'm taking this in the future is to take these cold core hot disk configurations and try to run them out to million-year time scale without affecting the geometry. So what I'm currently doing is turning SPH into sort of an implicit probe that will do diffusion and do radiative cooling off the surface of this disk, and account for the viscous torque at the same rate that I do those other two pieces of physics.
So
Yeah, there are a lot of people who.
Is something like that possible here?
Yes, but the thing is that those grid codes specifically are either 1D or 2D. If they want to run them at these long time scales. Once you get to 2D, you're usually running at higher than time scales. So 10 minus 2 seconds. And you want to run it after a million years. And you don't have the computing power to do that yet. So yeah, that's why I suppose I could do that even in a grid code, do what I'm doing now. Try to do the simplistic physics and grid code as well. But I don't think that's going to save you very much. I'm just hoping there's this to decay and to plot on the whiteboard is the kind of configuration I get. So there's always some data loss when you convert from one code to another, especially from part of another.
Well, if there, one of the issues here for us is when you do the pure hydro calculation, you may be missing a lot of physics like magnetic frictional stability and the rest.
Right. Yeah.
I'm not sure exactly. Doing radiation transfer in this complicated geometry is not trivial. In the double neutron star case, where you were very interested in neutrino transport, that really hasn't yet been fully done, just because it's so much more complicated to do it than in the body spherical geometry of the core cloud. And so, so one wonders whether a simplified 1D approach, putting in some of this more complicated physics by hand wouldn't necessarily yield some benefits.
Well, so the drawback to doing it in 1D, besides removing geometry, is then you don't know what the diffusion rate is. It's whatever you choose, right? And that's.
But other than you can't do the MRI, so this is the devil's advocate here.
Yeah.
But you can't do the MRI that we want to use, right? There's no way.
No, and
I do think it would be interesting in the first instance in just hours rather than, or a day, right? I mean, at least the scale longer that you can resolve. That's not needed in our paper. It's a very simple alpha estimate gives you in a few hours. Most of this should have agreed. That may be wrong. That's at least be interesting to check.
yeah, my suspicion is that I haven't actually done this yet because of what I just put now. That these timescales of diffusion and rate of cooling are going to be much longer than the timescales of decay. MRI is detail that I don't really want to get into, and I think it might only serve as sort of a perturbative effect.
Well, initially, you probably rely on self-gravity to help move this mass in. But once it gets below, 10 or 3% of the mass of the central star, that's going to not be very efficient.
That's true, but once I get to that configuration, that star will be super champs. So.
But that is what you could run on the
Yeah.
gentleman's.
Only because diffusion takes time. That's all I mean by that. I should run these pieces of physics that take millions of years in an explicit hydrogen acid.
One moment.
So yeah, these would then run on Kelvin essentially. And so these two pieces are done. Radiative cooling, this is very opaque. So radiative cooling is only happening on the very surface of this disk. So that was somewhat complicated problem to solve, but also somewhat simpler. And then explicit diffusion, that's just particle-to-particle thermal diffusion. And that was a fairly simple problem. So these are now running without viscous torque, just to see the kind of configurations they get to. And I don't yet have the results for that. And then in the further future, we're also looking at comparing the collisions that we did in SPH with what you would get in Flash, because people trust Flash for dots better than they do SPH. And so there's a parallel group at CC that is doing that. We also have in the works right now producing light curves from those collisions. And then eventually we would produce light curves from whatever we get from these mergers, these merger remnants. And then this disk, I mentioned, is extremely hot. It's 10 to the 9 degrees near the center of the disk. And so these should be producing some sort of X-rays, and that's going to transfer code to give us what that would look like. But that should produce some sort of signal. And it's roughly the size of the sun. This is roughly the size of the sun. And so at 10 to the 9 degrees across one solar radius, you should get something. It should be visible.
It will be limited by the adding, right? And right at the end. So.
Yeah, at the end, yeah.
But you're right, it should be a quicker signal, perhaps.
And then the final piece is to post-process the collisions and the merger remnants and everything we've done using much larger network codes to try to get spectroscopic signatures. So I mentioned before that really the only indicator I have that these are different from 1A is the collisions, especially is this uninverted carbon and oxygen. But there may be other isotope differences that you would see in the spectra that you would be able to distinguish both ways.
Again, I would have thought that if you emit at Eddington at the solar luminosity, that's only 10 to the 4 the solar mass, it's only about 10 to the 4 solar luminosities, which seems pretty faint to detect it, at any substantial distance.
If you emit at the Eddington
Is
limit,
that the limit? I mean, that's what Martin was saying. If the most you can radiate at for more than dynamical time
right?
is Eddington, then that's pretty faint. It's for a solar mass object that's 10 to the 4 solar luminosities.
Right. Yeah, I suppose that wouldn't be brightest of sources. Well, I haven't actually looked at detection possibilities. Just this is just something I'm thinking about. Could we detect this disk if you had an X-ray telescope? I suppose probably not.
We could also have a, function of one of these things that they blow up immediately, very rapidly within the star.
Yeah.
It's cooling like mad, so it's got a very heavy mass loss rate. So it's strong enough to go with mass loss rate. That makes potential for detectable light emission. I think you get almost potential. But that's a side assumption.
Well, anyway, that was the last slide anyway. So. Yeah, so that's work for the future. And that's what I am.
Plenty of time for questions if people want to ask further questions. That was the most succinct talk you've had in a while. You are a master of, anybody with all these questions about it.
Did I hear you correctly that you said you were thinking about putting implicit integration into SPH? No, that's not what you said.
That's, well, not implicit integration, but just these things that are typically done in implicit codes.
Yes?
So that diffusion and radiative cooling is in there now. And so I've done tests on that, and that is working. To have thermal diffusion between particles.
Yes, but you just mentioned that some timescale, all these timescales are very long compared to anything. But so why would one want to add it unless you also have implicit?
Yes. So the way that I mechanically do it is I calculate what kind of timescale will give me, say, a 10% energy change due to thermal diffusion, and then I scale up all those other physical processes by that amount, leaving hydrodynamics as it is. The idea is that shocks are not going to be important in this disk, and if they do become important, then I've done something wrong and I should stop the simulation anyway. And so hydrodynamics is fine and let it run at whatever timescale it wants to, but scale all these other things up so that diffusion is running at a